So I'm going to be talking today about a recent paper and the first part in a series of papers that I have been working on in collaboration with a group at the Canada-France-Hawai'i telescope, which is certainly a proud point in Canadian astronomy, with Laurie Rousseau-Nathan, Simon Prunet, Julie Clavachet-Laurando, et puis Sébastien Fabreau. And as mentioned, I work in Miriam's group in the physics and astronomy department. So just a brief overview of what I'm going to talk about. First, I'll talk about what the interesting physics that we're trying to study using machine learning is, which are known as H2 regions in galaxies. Then I'll move on to the new fantastic instrument at the Canada-France-Hawai'i telescope, SITELLE, that was actually developed primarily by a group at the Université de Laval. Then we'll look at some of the main results and finally discuss some conclusions. I normally, when I give this presentation, include a section on machine learning. I used neural networks, more specifically convolutional neural networks, but given the audience today, I don't have any slides on that. So I'm hoping everybody has a little familiarity with how convolutional neural networks work. So I like to motivate this by showing my favorite plot that I've ever made by querying the archive, which is really physics and astronomy's main database of papers. If you search machine learning papers in astronomy, and if you group that by year, you can see that the number of machine learning papers in astronomy have been growing exponentially over the past years. I'll admit that I haven't rerun this script in a couple months, so I can only imagine how much higher this last part of the histogram will be, but the trend is still incredibly evident. I threw some very interesting papers on machine learning and astronomy that I absolutely love, in case you want to read more about that. But it's really meant to show that there's a wide variety of machine learning applications in astronomy, such as image classification, learning things about radio astronomical images, or even, if you remember from linear algebra, eigenvectors. There is a similar thing in astronomy known as eigengalaxies and even eigenspectra. It's quite fascinating what people can do with really basic machine learning tools in astronomy. Okay, so it's astronomy, so naturally I have to show some very pretty pictures. One thing that I study are galaxies, and in galaxies there are regions known as H2 regions. These are regions of gas and dust that create these absolutely gorgeous images. You see here from the Hubble Space Telescope of the Pillars of Creation is a wonderful example, or over here the Spitzer Space Telescope took an image of this nebula, the Trifid Nebula, in multiple different wavelengths. H2 regions, like I said, are composed of dust and gas that is ionized by a group of young stars or just a single star that's incredibly hot. When I say it's ionized, that means the dust and gas in these regions are, oh, sorry, my cat stepped on my keyboard. The dust and gas in these regions are, he keeps doing it. Sorry. The dust and gas in these regions are being excited. The electrons in those dust and gas are being excited by the photons that are coming from that young hot star, young hot cluster of stars. Here you can see at different wavelengths, different features lighting up. So in the visible, you see these black bands. That's actually the dust that's obscuring the light. In the infrared here, you can really nicely see some of the stars at the center in that really hot region in the center, and over here in MIPS, those are the stars you're actually seeing at the center of these nebula. They're also known as birthplaces of stars because you have young hot stars and a bunch of gas. It's really the perfect place to create stars. This is just a little bit more on the technical side of things of what do you see when you look at these regions at different wavelengths. Well, what's happening, I really love this image. You have a big cloud of dust and gas. You have a star or a group of stars that are very young and very hot at the center. They are emitting a bunch of light, so a bunch of photons that interacts with that cloud of dust. These photons are highly energetic. They're normally in the UV, for those of you who are interested. And what that does is it ionizes the gas, which forces the gas to re-emit light at certain known wavelengths, depending on the composition of the gas, in what are known as nebular emission lines. So if we look at the spectra, which means the light signature from this gas, we just need to look for those emission lines and the peaks in the spectrum, and that'll tell us the composition of the gas. It also tells us a lot about the movement of the gas, so it's known as the kinematics. By studying the shifts of those lines and the broadening of those lines, we get a really good idea of obviously what's happening in the gas, how it's moving. We also learn a lot about the magnetic field strength and magnetic fields in the lines, which are in the gas, which can be really interesting. Yes, also you can learn about turbulence in these regions as well, just by studying those lines that are being re-emitted from the gas. How do we do this? My favorite instrument by far is that Canada-France-Hawai'i telescope. It is known as an imaging Fourier Transform Spectrograph. That's a whole bunch of technical jargon for it takes really beautiful spectra. It does a little more than that. Normally when you look at an object in astronomy, you're either going to get the photometry or you're going to get the spectroscopy. What does that mean? Photometry is the image that you see in normal coordinates. So if you were to look at the sky and see whatever you could see in the sky, you're looking at photometry. Spectra is the actual emission of light from that point in space. SITELLE and the class of instruments like SITELLE actually do both at the same time. They're a very unique class of instruments. So this is what's known as a SITELLE data cube. You have all the spatial information. For instance, this is actually a supernova remnant that you're seeing here. So you have the spatial information in X and Y coordinates, and in Z you have the entire spectra at each one of those pixels. And these are some typical spectra. I'll show you them again in a sec, some better images of that. SITELLE is really fascinating. It, like I mentioned, was designed by a group of students and professors at University of Laval, and it was tested at the Mont Mégantic Observatory that we have here in Quebec, a truly wonderful observatory. And then eventually it was moved over to the Canada-France-Hawai'i telescope on Mauna Kea, on the big island of Hawaii. Like I said, SITELLE takes spatial coordinates X and Y, and then also a spectra for each one of those pixels. Just, this should scare you if you're into computation. SITELLE has over 4 million pixels, which means there are also 4 million spectra you get to wade through. And last little piece, I'm part of a collaboration known as Signals Collaboration. That's Star Formation, Ionized Gas, Nebular Abundance's Legacy Survey. It's using the SITELLE instrument at CFHT to take images of over 40,000 of these H2 regions throughout the galaxy, or throughout the universe. This is just, this is an example of M33, which is one of the most famous galaxies for finding these H2 regions, or these star-forming regions. And these images were taken with SITELLE. The typical, what we normally see when we actually look at the spectra in SITELLE, depending on the bandpass that we choose to use. I'll focus on this. This is the third filter of SITELLE, third main filter. It's actually the main filter of SITELLE. It pulls out lines known as H alpha, N2, nitrogen 2, and sulfur 2. Those are just some of the emission lines. I won't talk about that, but I'll reiterate that from these emission lines and studying these emission lines, the widths and shifts of them, and also the strength of them, we can learn a lot about the interesting kinematics that are going on in these star formation regions. So great, I hope everybody has a decent understanding now of what we're looking at. So the question next is, how do we actually use machine learning to infer information from these spectra? I've mentioned the kinematics, meaning the velocity and broadening of the lines, which tell us a lot about the magnetic fields, turbulence, and general kinematics and dynamics of our system. So the idea is we want to take a spectra taken with SITELLE, feed it to some machine learning algorithm, and have that algorithm output the kinematic parameters, meaning the broadening and the velocity of the system. So our inputs will be those SITELLE images. We use a convolutional neural network to do our training and to actually do our machine learning algorithm. And then finally, we're outputted those velocity and broadening. As all of you, I'm sure, know, one of the most, by far the most important piece of machine learning is having an excellent training set. So we spent a lot of time building our training set. There's approximately 50,000 spectra in this training set used with software built specifically for SITELLE. We use a very sophisticated set of simulations known as the bond simulations to determine the amplitudes, velocities, and broadenings of these parameters. So it would be as realistic as possible and as applicable to real spectra. We use a standard convolutional neural network with 2 layers of convolution and 2 fully connected layers. We did not come up with this. We took this from Sébastien Fabreau's paper in 2018, where he used this for stellar spectra instead of H2 region spectra, but we apply the same idea. So just some results. On the left-hand side, this is a kernel density estimate graph for the residuals, meaning the true ground value minus the values for the velocity that our algorithm's spitting out. You can see in both of these that it does a pretty good job. There's some motion in here. It's not perfect, certainly, but it does a very good job of recovering the velocity, which is wonderful. That's a really interesting kinematic parameter that we want to know. The other kinematic parameter we try to extract from the spectra using the neural network is what's known as the broadening. And that really gives us a lot of information about the turbulence and importance of magnetic fields in those regions, in the star-forming regions. Once again, the results are very promising. We're really, really happy with that. So are the referees for the paper. You'll notice, however, for broadening parameters really below this 15 mark, it doesn't do too well. And that is a problem, but it's not a problem for SITELLE. SITELLE actually can't resolve lines beneath 15 kilometers per second. So it really doesn't matter if we can't do a good job of predicting them, since if we were to predict that, it wouldn't mean anything since the instrument can't even recognize it. But in regions above 15 kilometers per second, we do a very good job of recovering the broadening parameters. If you are familiar with convolutional neural networks or neural networks in general, one of the things you want to be able to do is say, well, my network's actually learning from the important features. Here I've highlighted the main emission lines that we're looking at, and the activation map with these darker dots is telling us that the network is primarily concerned with those regions about those lines, which is good. It'd be very worrying if our network was learning from all of this noise, but instead it's learning from the emission lines, which is perfect. This is really just a sanity check that we do. So I just want to show you some results on real object, on actual SITELLE observations. This is M33, that image I showed before. This is just a normal Hubble Space Telescope image of it. We took a region, this particular region of it, a southwest field. This is what it looks like. These are what those emissions look like when you stack them all together. So if you take the SITELLE data cube and compress it spectrally, this is what you would see. You can see that there's a lot of different regions. These bright pink, or sorry, bright yellow regions are the emission regions, and there's a lot of them in this map. We applied our neural network to it, and we realized that there were very bad systematics throughout our image. So you can see here, this is a residual plot for the velocity. There's a clear linear trend as you move up the cube, up the data cube. I'm only mentioning this because we were able to very quickly fix it when we realized that SITELLE, just the way it works, it's not a perfect instrument. So the resolution of these images aren't perfect at each pixel. And there's actually a linear function where the resolution changes. So taking that into account and retraining our algorithm with data that took that into account, we were able to recover really wonderful velocity maps in the end. It's just, I like to highlight this because it really goes to show you can spend a lot of time on your training set, but unless it's really perfect and tailored to what you're looking at, you're going to have problems when you try to generalize. These are the final residual maps just for broadening velocity parameters, those two kinematic parameters that we're trying to pull out. And the final thing I would like to say is that one of the major benefits of machine learning, why you would use this over standard techniques to pull out those parameters, it mainly has to do with the time it takes to do these calculations. And if you were to run on a supercomputer parallelized, or not supercomputer, computing cluster parallelized, the particular cluster we had 32 cores. To run normal fitting techniques, it took over 10 days. Running continuously, fully parallelized on 16 cores. When we ran our machine learning algorithm on a single core, it took only 4 hours on the exact same computer. So the time gained is immense. It's about 2 orders of magnitude to recover more or less the exact same results. So with that, I will stop. Hopefully you've learned a little bit about emission regions and how we can use machine learning to study their spectrum and pull out interesting parameters from that. So thank you very much.